Thank you very much. Thank you very much for the organizers for the invitation to this workshop and for the opportunity to talk here. Today I want to tell you, well, the talk will consist of basically two parts. In the first part, I will summarize some results on the geometry of null hypersurfaces from a fully detached point of view. And this is what I mean by abstract null geometry here. And then in the second part, I will use these results for an application related to the characteristic initial value problem. And for that, I will be using this constraint tensor that I will also introduce along the talk. Okay, so let me start by something that we all know, and this is the fact that null hypersurfaces have are very special for a number of reasons. The defining property of a null hypersurface is that the normal to the null hypersurface is at the same time tangential to the hypersurface. And this has several consequences. The first consequence is that the first fundamental form, which I call gamma here, is degenerate, with the degeneration direction precisely along the normal vector. And this implies that, of course, there is no canonical connection associated to this first fundamental form because it's degenerate. At the same time, the tangent space at any point on the hypersurface cannot be decomposed as a direct sum of a tangential direction, so the tangent space to the hypersurface, and the normal direction, because the normal direction belongs to the tangent space. So there is no direct sum. And this has another consequence, is that you cannot project covariant derivatives because you don't have a direct sum. And that's the second reason why you don't have a connection canonically defined on a null hypersurface. Nevertheless, null hypersurfaces are objects that appear in many places in GR and in Silver-Riemannian in Lorentzian geometry, and one would like to be able to do some geometry on a null hypersurface. So the aim of the first part of the talk is first to describe a construction that allows to do this, and then in the second part, as I said, I will present an application for the characteristic initial value problem. So let me start with the definition. So the key idea to do this construction is to encode the full space-time metric along the hypersurface and take care of the fact that there are many ways that one can do that. And since there are many ways one can do that, one has to take that into account. And in the end, what will happen is that one introduces a gauge group on the object. So the definition is as follows. So I will say that a metric hypersurface data is the following: is a manifold, an n-dimensional manifold n, with a symmetric 0-2 tensor gamma, no conditions on it. It can be degenerate or non-degenerate, anything. And then there is also a covector L and a scalar L squared. So this four tuple, this collection of four objects, is what I will be calling metric hypersurface data, provided the following happens. So at any point on the manifold, you can build the following vector space. You take the tangent space to the manifold and direct sum it to R. And then you can construct a symmetric 0-2 covariant tensor on this space. This is a vector space of dimension n+1, by simply this construction here. And what this tells you is that, of course, an element in this vector space will be a tangential vector to the manifold, and a real number at that point. And you take a pair of those, and you pair them with this tensor A. This is going to be a symmetric 0-2 tensor, so a quadratic form. And the way you pair them is the vectors, you pair them with gamma. The vector y and a, you pair them with L, and then symmetrize. And then AB, you pair with L squared. So it's just a way of putting together all these three objects into one symmetric 0-2 tensor field on a one dimension higher. And what we ask for this collection to be metric hypersurface data is that this symmetric 0-2 tensor is non-degenerate at every point. We will say that the data is null by definition if gamma is a degenerate symmetric 0-2 tensor. Okay, so if you can think of this as follows. You can think of A as a matrix in n+1 dimensions. So you have a m times n block gamma here, the one m block L here, the transpose here, and the scalar there. And what we are asking is that this symmetric, this matrix in this language is invertible, is non-degenerate. Okay? And since it's invertible, you can invert it, and you can then read off the different components in this inversion. This would be now a 2-0 tensor. Now the P part will be then a contravariant tensor on N. N will be then since this was a 0-2 tensor, so a covariant tensor, P is going to be a contravariant tensor in N. L was a covector, N is going to be a vector on N. L squared was a scalar, N squared is going to be a scalar on N, just by construction. And it's an immediate consequence of the construction that the hypersurface is going to be null. That means gamma degenerate, if and only if this scalar N squared is 0. Okay? So, and you should think of this just really as encoding a metric in n+1 dimensions along N. Okay? So this is all very, very natural in some sense. But the thing is here is that this definition is completely abstract on N. So I'm not talking about any space-time or any ambient manifold where this is sitting. It's just something that you define on its own. To make connection with the hypersurface case, one needs something called a rigging vector. Rigging vectors is something that was introduced many years ago by Schotel already in '54, and it's something also very natural. One calls a rig. If you take a hypersurface H and you assume that this hypersurface is two-sided, then you define a rigging vector xi as a vector field along the hypersurface, which is everywhere transverse. Right? So since it's two-sided, you will have such a rigging vector, and with this definition, you can connect these two quantities by the following definition. So we will say that metric hypersurface data is embedded in some ambient space. This is going to be a space of dimension n+1, and G is going to be a metric on of the signature that's appropriate. And we will say that this data is embedded in this ambient space if there exists an embedding, phi, that sends n into M, and the rigging vector, psi, one of such transverse directions, such that the following happens. First, gamma is the first fundamental form, so it's the pullback of the metric. L, this covector, is just the pullback of the covariant of the covector that you construct from psi, which is a vector field, if you lower its indices. So this is the metrically related covector to psi. You pull it back, and this should give you L. And L squared is just the square norm of this rigging vector. So in this expression, it's clear then that what gamma is, you should think of gamma as the tangential directions of the ambient space metric. L encodes the transverse tangential directions of the ambient space metric, and L squared is just the transverse component of that metric. And it's then a very simple computation to show that this vector nu, which is just the push forward of N plus this combination with the rigging, is actually the normal, or the normal to the hypersurface that satisfies this condition. There's only one normal that satisfies this condition, and it's given precisely by this fact, by this quantity. And note in particular that when N squared is 0, then the N vector is just, N is just the normal vector, which in this case is tangential. So N and nu, you should think of them as the same thing in the null case. So N is then a null generator in the case of null hypersurfaces. Okay, so of course this construction of course has a lot of freedom in the fact that the rigging vector is something which is not unique, and this is the sentence I was saying at the beginning, that there are many ways of encoding the n+1 metric into N. And we need to translate this freedom into the abstract definition. And we do that by means of this notion of gauge transformation. So we define what a gauge parameter is. A gauge parameter is just a pair ZV, where Z is a nowhere zero vanishing function. F star here means the set of nowhere zero vanishing functions on N. And V is just a vector field on N. Now, if you take a hypersurface data set, gamma L squared, one can define the transformed hypersurface data set with this gauge parameter ZV by these expressions here. And these expressions have the following properties. If you start with something which was metric hypersurface data, the transformed quantity is also metric hypersurface data. So you don't go out of the space. And this transformation defines a group. So, and the composition law for this group is just multiplication of the first entries, and it's a direct sum, it's a semi-direct sum of the second entries. Okay? And that means that what one has here is now is a collection of metric hypersurface data for each, for the manifold N, and we will identify these two quantities whenever they are related by a gauge transformation. So in that sense, we will consider metric hypersurface data related by these gauge transformations as geometrically the same quantity, and we will call them metric hypersurface geometric data. Okay. Now the question one asks oneself is, okay, what can you do with this kind of construction? Now it turns out, and this is the key result actually, in order to be able to do geometry on this abstract setting for hypersurfaces, is that you can define a canonical torsion-free connection. And this connection is defined as follows. Out of the data, so out of gamma, L, and N squared, you construct another symmetric 0 to tensor U. If you think in the case of the null case where this term vanishes, it's just the Lie derivative of gamma along N. So it's just something that you construct along taking the derivative of gamma. And then what it turns out is that you can define a unique torsion-free connection that satisfies these two equations. So the explicit expression doesn't matter so much. What matters is that these two conditions are compatible in the sense that you can definitely show that there is one connection that satisfies that. And note also that in the standard case where you have a non-degenerate first fundamental form, a metric, what you would ask is that this connection is metric, so you would be asking that this is 0. This is a generalization of that, and this generalization is consistent in the following sense. First, since the connection is unique for each metric hypersurface data, I can now change the data by a gauge transformation and just compute how this connection will transform. The result is this. Again, it doesn't matter the explicit form. It's somewhat complicated. It has some quantity that goes along the gauge vector V, and some quantity that goes along this vector N. But what's important about this is that this transformation realizes the gauge group. So if I take one of such connection and I do a gauge transformation with parameters Z2, V2, and then I do another transformation with parameters Z1, V1, the result turns out to be the same as doing the transformation with the composed element. So in this way, with this construction, what one does is one endows the manifold N with a family of connections, all of them related to each other by a gauge transformation. And it turns out that when gamma is non-degenerate, there is a gauge where this connection agrees with the Levi-Civita connection. So in that sense, it's a generalization of the Levi-Civita connection in this much more general setting where gamma is allowed to be degenerate even at every point. Yep. No, it's not. No, it's not. I will tell you what the gauge group, the geometric interpretation of the gauge group in the next transparency. Not in this one, in the next one. So just bear with me for a second. So a hypersurface embedded in some space has intrinsic information and extrinsic information. So far, we have only been talking about the intrinsic information because everything has been, encoding the metric at the level of the hypersurface in an abstract way. So what about the extrinsic information? The extrinsic information is encoded into, you can expect that, into a symmetric tensor Y, symmetric 0 to tensor Y, which plays the role of second fundamental form, if you like. And we will define then hypersurface data as just a collection of objects where the first 4 objects define metric hypersurface data, and you add to it a symmetric 0 to tensor Y. And the only thing that we will require for this object is that it satisfies a certain gauge transformation. So its gauge behavior is prescribed to be like that. And then one can give a simple geometric interpretation to this Y in the embedded case as follows. We will say that one such now metric hypersurface data, which now includes this Y tensor in it, we'll say that it's embedded with embedding phi and rigging psi when, well, first, the first condition, of course, has to be met. So the metric part is embedded in the sense I was mentioning before. And on top of that, the Y tensor is just the pullback of the Lie derivative of G along psi. So what does this mean? Psi was a transverse vector. So this Lie derivative is a transverse derivative of G, and now you pull it back to the manifold, and therefore it gives you transverse information about extrinsic information about the geometry. Okay. Now going back to your question, the rigging was highly non-unique. We intended to encode this into the hypersurface data information by the gauge group, but these two things have to be well connected, and this is what this result tells you. It tells you that if I have one metric hypersurface data in an ambient space with some embedding and rigging psi, then if you gauge transform the data in the way I've defined before, then it turns out that this data is embedded in the same space with the same embedding, but with a different rigging, which is just this object here. So what this is doing is moving the rigging to any other possible riggings to every possible transverse vector field to the hypersurface. And there's only one way. So, you know, the possibility is to define, given one transverse vector, any other transverse vector is possible to be written as a factor, you know, a function times psi, with this function being non-zero, so that it remains transverse, and anything which is tangential. Okay? So, and this allows one to connect this nabla zero connection that I was introducing before at the abstract level with the connection in the ambient space. The ambient space now has a metric, so it has a Levi-Civita connection. How does one do the connection between these two things? Well, it's very simple. Since we have a rigging vector, this allows you to now decompose any vector field along n into transverse components and tangential components. So any vector zeta along n will be decomposed into a scalar times the rigging vector and a tangential vector. And you can also do that for the covariant derivative of two vectors. If you take this covariant derivative of two vectors and take the transverse part, which is going to be a scalar, which is going to be, well, actually I should drop, with this definition, I should have dropped this psi here. But nevertheless, so you can take the tangential part, and the tangential part is the more interesting one. It tells you precisely what this nabla zero is. What this nabla zero means is, if you take the covariant derivative of two vectors along n, x and z are tangential to the hypersurface. Now you take the derivative of one along the other. This does not preserve the property of being tangential, so in general it will have a transverse part. But the tangential part, which will depend now on the rigging, of course, because if I take another rigging, the tangential part will also change. Then the tangential part will decompose with this nabla zero connection, and everything else is related to the extrinsic information y. So what nabla zero is the part of the parallel part of the ambient connection when you drop the y dependence on it. And that's why it depends only on the metric part of the data. So that's the interpretation for this nabla zero connection. Okay. Right. So from now on, I will restrict myself to the null case because it's the one that I want to, because the application is related to this one. So in that case, I will therefore restrict to the case where the signature has 1, 0, and the rest can be pluses or minuses, but it only has 1, 0. Okay. Now it turns out, and this is remarkable, that in this case, a manifold endowed with a degenerate metric in this sense is everything one needs to define null metric hypersurface data. And the reason for that is the following result. If you give me two such null metric hypersurface data, it turns out that they are always related by a gauge group element if and only if gamma 1 and gamma 2 are the same. So as soon as gamma is the same, whatever you add to the metric hypersurface data, you can relate to whatever you want. And any two things that you give me, they will be related to each other. So essentially, the information is in gamma. That's of course, very, very interesting. But the question is, okay, what if you just give me gamma? can I construct metric hypersurface data? Because this result only tells me that two such metric hypersurface data is going to be related. But can I build a metric hypersurface data? And the answer to that depends on the behavior of the radical. So you know that given a degenerate metric gamma, you can define the radical, which is the collection of vectors that get annihilated by gamma. This is one-dimensional because of this property here. So at every point, you have a one-dimensional vector space, right? At the tangent point, at the tangent space, at any point, you have a one-dimensional distribution, and this distribution then can have one of two things can happen. This defines a line bundle. Either the line bundle is trivial, so it admits a global section, or it is not. If it's trivial and hence admits a global section, then you can define metric hypersurface data in this space. And in this metric hypersurface data is actually then uniquely defined by gamma because of this first lemma. And if not, if the line bundle is not trivial, then you cannot define metric hypersurface data. And you can think, okay, maybe then this is a drawback. But it turns out it's not such a bad thing, because even though there is no global section, you can still work with local trivializations for this line bundle. And in the local trivializations, what will happen is that in the transition between in two overlapping open sets, you will have transition functions that basically will either keep n invariant, or it will swap n to minus n, right? That's what it can do. But if it changes n to minus n, it nevertheless does not change the connection gamma 0, because gamma 0 has this property, nabla 0. The connection nabla 0 has this property. So swapping n to minus n is exactly the same as applying the gauge group element minus 1, 0. And it turns out by the definition, by the construction, that this connection remains invariant under this gauge element, this gauge group element. And therefore, even though you cannot define a global cross-section, and therefore you cannot define globally metric hypersurface data, you can still define a connection on this space. So the conclusion is that if you give me any manifold n with a symmetric 0-2 tensor with this signature, I can define a collection of connections on that manifold and a gauge group on that manifold that acts in a precise way, in a specific way. So in that sense, that's why, to me, it makes sense to call this null geometry, because it only requires a manifold n and the degenerate metric symmetric 0-2 tensor with this signature. Okay. Okay. I presume I need to be. I'm a bit slow. So okay. So let me now introduce the constraint tensor. What the constraint tensor is just okay. It turns out that if you give me embedded hypersurface data by, it's just a generalization of the standard Gaussian Kodacci identities, that you can compute the following components of the Riemann tensor: the fully tangential components of the Riemann tensor, and the once transverse and the rest tangential components of the Riemann tensor can be computed in terms of the data. This is just the standard Gauss-Kodacci identities. And in this case, slightly generalized because the hypersurface is of any causal character, but nevertheless, this is still true. Now, from these two tensors, you can do certain contractions, and it turns out that this combination can also be computable, is also computable in terms of the data. So, and this combination is interesting because it has something which is transverse, transverse, tangent, tangent, but it's multiplied by the square norm of nu, and nu was the normal vector. So when the normal vector was null, and therefore the hypersurface is null, this term is 0, and what this is telling you is that the tangential components of the Ricci tensor can be computed in terms of the data. And then it's a computation to find out what this object is, and then once this computation is done, you can promote the result to a definition. So I will define the constraint tensor as this symmetric tensor. Again, the explicit expression doesn't matter. It involves all the dependence on y is completely explicit. So kappa is the nn component of y except for a sign. R is the n component of y whatever else is a covector, and so on. But never mind about the expression. This R0 is the curvature of this connection nabla 0 I introduced before. And the interest of this tensor, which is defined on its own, so it's defined at the abstract level. You give me metric hypersurface data, actually hypersurface data, and I compute this tensor. I don't need this object, this manifold to be embedded anywhere to compute it. But when it is embedded, it's encoding the Ricci tensor of the ambient space because of this property. This property is the one that actually brought us to this definition. Okay. So, and this tensor R, this symmetric tensor R, will play a fundamental role in the application I want to describe, which is the characteristic an application for the characteristic initial value problem. And everything I will be saying from now on is joint work with my student Gabriel Sanchez Perez. Let me start by reminding you something that you all know, and it's the fundamental theorem of existence of solutions of well-posedness of the Einstein vacuum field equation by Madame Choquet-Brouat from 52. And that says as follows. So if you give me an n-dimensional manifold, a metric H, a Riemannian metric H, and a symmetric 0 to tensor K that satisfy the constraint equations. You all know about these constraint equations. It's Hamiltonian constraint, the momentum constraint. And then, and only then, so when these conditions are satisfied, and only in that case, there exists a space-time of one dimension more, which is a solution of the lambda vacuum field equations. So it's an Einstein space with cosmological constant gamma. And in this space-time, you can embed your data in such a way that the first fundamental form of the hypersurface is H, so it's embedded as a space-like hypersurface, and the second fundamental form is precisely K. So you see, the data is given in a fully abstract way. Sigma n is a manifold, H is a metric, K is a symmetric 0 to tensor. A posteriori, this is embedded as a space-like hypersurface. So the initial data is given in a completely detached way from the space-time one wishes to construct. Now, in the characteristic initial value problem, one, instead of giving initial data on some space-like hypersurface, like here, one gives initial data on two null hypersurfaces which intersect transversely on some surface. Sorry. Yeah, on some surface here. So you have two null hypersurfaces that intersect transversally on some codimension 2 space-like surface here, and then the Einstein vacuum field equations tell you that you have a solution in the wedge contained between the two null hypersurfaces. So the well-posedness of this characteristic initial value problem has been proved in several contexts. The basic result is by Alan Rendell in 1990. And he showed that given data on two null hypersurfaces that intersect transversally with data appropriately given, there is a space-time that realizes this data. So if the picture will be like that, so this would be, say, H, this would be, say, H bar. This is the surface S. And Rendell's theorem guarantees existence of a space-time in a neighborhood of S. So in some neighborhood of S, not all the way, not covering all H or H bar, just in the neighborhood of S. Now this theorem is for two null hypersurfaces that intersect on some surface S. This was extended to the case where the initial data is given on a future null cone issuing from a point. This is a theorem by Choquet-Brouat, crucially Martin Garcia from 2011. Now in dimension 4, this theorem, and in dimension 4, this Alan Rendell's result can be extended. This was done by Jonathan Luke and then Cabet, Crucial, Wafo, in the sense that you can then prove existence of this space-time not just in a neighborhood of S, but in a neighborhood of the whole initial hypersurfaces H and H bar. So in any case, in all these works, the data was given as fields on the boundary of the space-time that you want to construct. So in that sense, it's not at the same level as the geometrization of the standard Cauchy problem, where you give data from in an abstract point of view, in a detached point of view. So the aim of what I want to explain in the remainder is to achieve for the characteristic initial value problem a similar geometrization as for the standard Cauchy problem. So we already know how to define abstractly a null hypersurface. So okay, we have a first step towards what we want, but we need to be able to define not just one null hypersurface, but actually two null hypersurfaces that will eventually intersect transversally. And you need to do that in an abstract way, without referring to the space-time you want to construct. And to do that, you will eventually, in order to be able to say, in order to say at some point that these two null hypersurfaces intersect, you will need to relate, you will have, say, some h with some boundary on, actually n, because it's already abstract, with some boundary of n, and another one, n bar, with some boundary n bar. And what you want to do is to impose certain compatibility conditions on these boundaries, so that it will eventually allow you to identify them in the space-time you want to construct. And to do that, one needs to be able to define some extrinsic geometry, because identifying this will require some extrinsic geometry information at the abstract level. And the object that allows you to do that is this notion of normal pair. So a normal pair is just a function. So you give me a submanifold S at this point of any codimension. So give me one of these metric hypersurface data, give me a submanifold, embedded submanifold of any codimension. Now, normal pair, what is it? It's just a scalar function on S and a vector field along S, not tangential to S, just along S. Now, this pair is called a normal pair if it satisfies this condition. Now, this is a linear condition, and it's easy to show that if the dimension of S is k, then the dimension of the set of normal pairs forms a vector space. This is immediate because it's a linear relation. So that forms a vector space. And the vector space has dimension n minus k, where n is n plus 1. So it has the codimension of S in n plus 1. This is the dimension of this collection of normal pairs. Now, what is the geometrical interpretation of this? It's very simple again. If you give me a normal pair CT, and we are in the embedded case already, so I can talk about spacetimes or ambient manifolds and so on, I can then push forward this T vector, and I can add it C times this rigging vector psi. This, of course, is a vector along phi of S, and this vector is a normal vector to phi of S. So I'm just, again, encoding the information about the normal vector into some function and some vector. Okay. And now, what allows one to do, this notion of normal pairs allows you to introduce at the abstract level what eventually is going to be the second fundamental form or the torsion one forms of the embedded submanifold, but at the abstract level, at the detached level. So one defines this tensor KT. Again, never mind about the definition. And one defines for a basis of normal pairs, for each pair, you take a basis of normal pairs, and for any two of them, you define a covector with this rather long expression. Again, doesn't matter the explicit form. But what matters is that this definition is such that when you embed the data, when this data is actually embedded in the sense I was mentioning before, then the image of your submanifold will have second fundamental form, which is precisely KT along the normal direction T, and we have connection one forms of the normal bundle given by these covectors. Okay, so you are encoding this ambient information at the abstract level. Okay, so so in order to deal with this characteristic initial value problem, I need to restrict myself to a certain topology, because this by construction has topology S cross R. And this is what this is telling you. So I'm assuming now that I have a manifold with boundary, that I have the right signature, so it's 0 plus plus 1, plus 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 1, 0 plus plus plus. And I'm also assuming that I have a function u which defines the boundary and which defines also a foliation of the manifold n by sections. Okay. Now, by this condition here, it turns out that the boundary induces from gamma induces a positive definite metric h. So the boundary induces a positive definite metric h. And now for the initial value problem, as I said, I need a way to make the two data compatible. And the object that allows you to do that is this boundary isometry object. So the boundary isometry by definition is the following. So if you give me two, by the way, this is called to summarize these three properties, I summarize them with the name characteristic hypersurface data. Okay? So if you give me two characteristic hypersurface data, we will say that they are boundary isometric, provided, well, first, the boundaries have to be isometric in the sense that the induced metrics, there has to be an isometry between the induced metrics. And on top of that, you want that at the level of this vector space where actually the A tensor at the very beginning was defined, you want to be able to define an invertible linear map at this level. And these two things have to be compatible. So when psi takes something which is already tangential and no transverse direction, it should do just what phi star does, so the push forward. And the metric, this invertible tensor A bar should be pulled back from n bar to n by psi. And in that sense, this defines a boundary isometry. And this is the object that will play a crucial role. Now, it's a simple fact that if you give me an isometry between the boundaries, the collection of boundary isometries is parameterized by a nowhere zero function mu. So once the isometry phi is fixed, the collection of boundary isometries is identified by this object here, which one can show is something which is non-zero. Now it's already clear what one needs to do, because now we have the boundary isometry that allows you to transfer information from one side to the other side, and therefore the definition is now completely natural. It's just the only thing that you can think of. So we will say that two such data define what we call double null data when there is this compatibility, and this compatibility tells you the following. So recall that K was the second fundamental form. So you can take the second fundamental form along the image of a normal pair, and then you can pull it back. This gives you something which lives on the first space, and it has to be, you ask, that it agrees precisely with the second fundamental form of the original vector. And the same, similarly, for the torsion covectors. These are the two conditions that you would expect naturally. There is a third condition that you need to impose, and this is that this constraint tensor is also the same viewed from one side and from the other side. Okay? Of course, this has to be because this R tensor is the Ricci tensor when you are embedded. You know, it has to be the same in the end. So better ask for it to be. Okay, now when this happens, we will say that this defines double null data. Okay, so this definition has several nice properties. First, the definition has been given in terms of a basis, but the definition is independent of the basis. You can show that, and it's gauge invariant. So, and if it happens in one gauge, if the definition is true in one gauge, it's going to be true in any other gauge, as soon as you prescribe that this function mu that defines the boundary isometry transforms in this form. Now, if you recall, the compatibility conditions that come in here are of zero order, because it involves h, first order, because it involves extrinsic curvature, and second order, because it involves curvature. Now you can ask yourself, okay, is it necessary to go to higher order? Do I need to impose additional restrictions in my definition? And the answer is no. And to be able to answer that, I need the notion of embedded double null data. The definition is completely natural. So once you have double null data, you will say that it's embedded whenever each of the two sides is embedded on its own and the boundaries agree, right? So now you have boundaries and you want the two boundaries to actually go into the same place, so that in the embedded case, the two null parts are actually, you are describing really two transversely intersecting null hypersurfaces. Now this would be a picture here. And so whenever one says that some double null data is embedded, it means that it's already put in the space-time in this form. Okay. Now, as I said before, there is no need for any further conditions, and the reason is this result here. It tells the following: if you give me any double null data, I can always find a space-time embeddings and ringings so that this double null data can be embedded. So that means that there are no extra conditions I need to impose, because whenever you give me those conditions, I can already construct a space-time where it can be embedded, okay? Note that this space-time MG here does not satisfy any field equations. This is only to answer the question, is it sufficient, necessary, and sufficient? And the answer is yes. So there is a space-time. Whenever there is a space-time, I will call it a development of the data, okay? So give you double null data. If there, to any space-time where I can embed that, which now I know it can in some, so therefore in many, any of those will be called development, okay? Now I can, one already has all the ingredients for the geometrization of the characteristic initial value problem. These are the lambda vacuum field equations, you all know them. So the question asks, what are the necessary and sufficient conditions for some double null data such that there exists a lambda vacuum development? So under which conditions the double null data is going to be embeddable in some vacuum, lambda vacuum spacetime? Of course, there are a couple of conditions that are necessary from the start, because this constraint tensor R was just a pullback of the Ricci tensor, and now it's lambda vacuum, so the Ricci tensor is proportional to the metric. Therefore, these are definitely necessary conditions for this. This is the equivalent to the Hamiltonian and the momentum constraint in the standard case, and we will call these abstract constraint equations. Now, the main result is that these conditions are not only necessary, they are also sufficient. So if you give me double null data that satisfies these abstract constraint equations, then there exists a lambda vacuum development of this data. So there's a way of characterizing the conditions that need to be satisfied by the double null data in a way which is completely independent of the space-time that you want to construct. You can write it down on its own without referring to the space-time. Okay, I'm really running out of time. So let me just tell you very briefly about the uniqueness part. So you want to ask the following question as well. So of course the solution is never going to be unique, because if I apply a diffeomorphism to the data, I will be getting another solution of the same of the Einstein vacuum field equations. So the best you can ask for is some geometric uniqueness. And in this case, the question you want to answer is, what are the necessary and sufficient conditions on the data that guarantee that the solutions are related by a diffeomorphism? Okay? Now, in the standard case, the answer is well known, so I will basically skip on that. The answer is, if you give me data which are isometric and which send the second fundamental form of one into the other, then the future developments are isometric, if and only if. So that's all well known and expected. So let me just finish with this statement. Now, in the null case, in the characteristic case, you cannot just say that the two data are the same, because we have the gauge group playing built in all the time. And two data that are related by a gauge group element, they are the same. So you have to incorporate this fact into the very definition of when you will say that two double null data are going to be isometric. You will say that two double null data are going to be isometric when there are diffeomorphisms of each one that bring the data of one into the other in the completely natural way. But in the sense that the result is not the same data you started with, it's just the same data you started with up to a gauge group element. the natural thing. And now in this, once you have this right definition of isometry at the level of the data, you can prove the local geometric uniqueness, and with this I will finish. So if you have two double null data which satisfy the constraint equations, and you have now two respective developments of them, then the developments are going to be isometric on some neighborhood of the boundary, if and only if the data that you gave me are isometric in this sense. And I'm sorry because I'm a bit late. Thank you very much.